So here, how we got this transition is just by multiplying and dividing by this. And if you remember, this quantity was a unit vector. So when you squared it, you just get a 1. So essentially we're just doing a change rule here and changing from, basically we're doing this. We're doing partial x, partial sigma, times this quantity, that is like the length of the string, the physical quantity we defined before. And basically this thing is gonna be 1. So then this just gives you this. Or you can also write it as a full derivative. Cool. So that's what we did for this step. Okay. Then, if you trust me, you can also simplify these two expressions to this form. You can try it. But I think they didn't change much. They were already simplifying that last lecture. And we're going to simplify it even more pretty soon. So cool. Okay, so this is our current expressions that are simplified. Now let me go to the relativistic, or sorry, physical interpretation. Physical interpretation of the equation of motion. Cool. So let me just write the equation of motion for you to remember. This is the equation of motion. I'm just moving one term to the other side. Cool. So if you consider the 0 component, so let me make only the first component. Then it's going to be equal to this. There you go. Sigma 1 minus speed c squared. Cool. And then we know that if we take a partial, then this is going to be equal to 0, because nothing here depends on tau or time. So essentially what this is telling us is that this quantity that is inside here is time independent. Cool. So what is the meaning of this? Like that this quantity is time independent? So if we take a string, or like a d sigma piece of string, then the quantity here is going to be constant in time. So this just stays constant in time. And in previous chapters, like in the second lecture, we saw that the energy of the string is equal to, like whenever we had the stretch string, I think it was the third lecture, the energy of the string was this, equal to the tension times the length of the string. So now we're seeing like an infinitesimal version. We're seeing we have the tension times like an infinitesimal part of the string, and all of this is multiplied by a gamma factor. As you can see, this is a gamma factor. So this can be identified as the total energy of the string. So essentially we can write, if you want like the energy of a piece of a string, it can be written like this. Cool. So that's like the physical interpretation of this part. And this formula we're going to actually use it in a bit, so just keep it in mind. And in your homework, in homework 4, I put you an exercise to show that a Hamiltonian is equal to this for a relativistic string. And you can show this. So yeah, so it makes sense to talk about the infinitesimal energy to be this quantity. Cool. So that's the meaning of one part of the equation. Now if we do the special components, let me take the special part. It's going to be equal to this, 0 d sigma. Oof, there's going to be a bunch of manipulation here. Okay, cool. So then we have this one and also this other component for the big P sigma. Okay, so we can plug back these two equations. I'm just basically just taking the indices from these equations. We can plug it back to the equation of motion. And if we plug it back, let me just show you, because this is going to take a while to write it. You plug it back to the equation of motion, and then we can simplify. We can make simplifications here, which is basically we're just putting the time derivative inside. And you can also define effective tension and effective mass, or mass density. And essentially this puts our equation into a wave equation form. And why is a wave equation? Because this, if you remember, is equal to this partial derivative. So essentially you get equation of motion for a wave equation, which was expected, since you remember we did first the wave equation and then we put it in Lagrangian form. But yeah, we're just confirming that the stuff it's like that our model is accurate to what we expected. So that's good. And oh yeah, another important fact about this is that if we take, let me just show you these two formulas for the effective tension and effective mass density. I'm gonna start copying and pasting some stuff so that I don't take that much time to finish all this. Cool. So basically what this is telling you, if the only way to get tension equal to 0 is when you get speed of light. So essentially the reason why the endpoints need to be at the speed of light, like if you don't buy the previous explanation that we gave, is since arbitrary, then the endpoints have to be at speed of light at c, because it's the only way to be free. It's the only way to not have like a tension for this quantity to be 0, because we want them to be 0. Cool. So that's like the explanation I can give you of why the endpoints have to be the speed of light. Cool. Okay, now we can do some simplifications and get some fundamental string equations. These fundamental string equations are going to be 4 equations that we're going to have to solve every time we want to solve for like a string system. We're going to see one of these examples next class. The beginning of the class is going to be just an example of how we can solve one of these systems. So actually, let me see if I'm going to take a while to write all of this. Let's see. Yeah, this is going to take a bit. Cool. Okay, let's do it. Okay, so we want to simplify our equations more. So the goal here is going to be derive fundamental equations for relativistic string. And the way we're going to do simplifications is we already parameterize the string like using the tangent sigma parameterization. But we can also parameterize by doing something that is choosing that each segment, like each sigma segment of string has equal amount of energy. So it's like basically having the energy be distributed uniformly to the string uniformly energy. I don't know if this makes sense, but yeah, I'm gonna write the expression mathematically, and that is gonna make sense, I hope. So the way we're gonna do this, first we can rewrite our equation star 2. Let me call, where's my star 2? Yeah, I should have written this. Okay, cool. Let me just copy it from here. So whenever we plug in these expressions in the equation of motion, then we get this equation. Cool. Okay, so from here we can do some simplifications. One of the simplifications we can do is first rewrite it in this way. We can do 1 over c squared, t squared, cool, 2. There's many steps in this little simplification. Try to stare a bit to it for a minute, and then if you don't see what simplifications I made, then I'm gonna try to explain. Cool. Okay. So this is the expression we get after doing some simplifications. Most of the simplifications were just moving stuff around, and this allowed us to define a quantity called A. This quantity A is just gonna take this form, ds over d sigma square root of 1 over the transverse speed or transverse velocity square over c square. Cool. And then this is gonna allow us to replace it here, and we're gonna get this expression over a sigma. This A quantity is not gonna be that relevant, so you don't have to remember. It's just to make a point. We're just gonna make the point that now we can define like a new coordinate. We're gonna define it this way. A sigma, D sigma. Cool. So then this is gonna allow us to put this equation into a wave equation form. You see, this is a wave equation. And cool. So if we see the parametrization, then this sigma prime is just gonna be equal to ds over square root of b transverse over c squared. Why? Because just replace this thing here, and you're gonna see like this d sigma simplifies with this d sigma, and cool. And if you remember, this is the same as the energy, like this whole term, but we have to divide it by T0 because we had our definition of energy here. Yeah, but it was missing the T naught, the tension. Cool. So basically how we're gonna parameterize everything is using this sigma prime parameterization. And if we want to define it more formally, it's like for every point, the sigma prime coordinate is going to be equal to the energy divided by the tension. So what this means is if you have a string, let me draw this, and I have a point, this is a point Q, sigma is going to be the amount of energy there is from here to here. So essentially when you get to the maximum, like to the maximum length of the string, you're gonna have all the energy. So we're gonna have sigma prime to go from 0 to sigma 1, and sigma 1, like the other end, is gonna be E or T0, that we know is like the total energy of the string. All we know is the number we're assigning to be like the total stretch of the string. Yeah, so essentially when you have sigma, or like you have 0, sigma equal to 0, then it's gonna give you 0 because there's no energy at this endpoint until you start like going throughout the string. So this is a way we're gonna be able to simplify more the equations. And essentially now the sigma previous that we're using, we're just gonna call it like this sigma prime is just gonna have the name sigma, and you can forget about the previous sigma because this is like a better parameterization we're gonna use. Cool. So we can also show that orthogonality holds, like the property we care about, this thing holds like with the new coordinate, so that's good. And now we can do some simplifications. Now we can rewrite the sigma prime. We're gonna find some fun stuff that's gonna be very useful. If you just move terms around, then you can put this equation of, this is just the parameterization, the sigma, into this form. The sigma prime square plus 1 over c squared b transverse equals 1. Cool. And then we just replace b transverse by its expression, that is like this. And we're gonna replace this, well, let me just write it here. So we're gonna use that this is equal to, this is just our previous definition with some simplifications. And also this expression is the same thing I did before, just replacing, doing like a chain rule, and then you get this equality. I think we used this equality a couple of times already, so just make sure you remember that you can relate ds to the string coordinates. Cool. So then this gives you a very useful expression. This is going to be one of our fundamental equations. 1 over c squared. Cool. Equals 1. And we're going to call this the parametrization condition, because essentially our sigma parametrization is imposing this condition. So it's just the parametrization condition. Cool. And now let me analyze the boundary conditions. We're going to try to derive the other 3 equations now. So if we go to the boundary conditions, then let me take a look at this quantity. Cool. 1b squared c squared the sigma prime ds. Cool. So this whole thing is going to be 1. Why? Because if you have a sharp eye, you can notice that this is the same as the sigma prime. So then this is just 1. Cool. So this allows us to write this big P sigma spatial components as just minus T naught and the partial with respect to sigma. Cool. So essentially the free endpoint boundary condition now is going to be simplified. The free endpoint boundary condition that, if you remember, was just making this equal to 0 at the endpoints. Boundary condition now is going to be the same as saying that the partial with respect to sigma is going to be equal to 0. Cool. So this is going to be simplification. And okay, so now we can put all the equations in motion, all the fundamental equations together, because we already had to. And let me just copy and paste them, so I don't have to. Let me just copy and paste this whole thing. Yeah, we're doing a bunch of simplifications. This is just the derivation of how we're gonna get to all the things we care about. The course essentially is 2 halves. The first half is just gonna be us, as we're doing now, and we've been doing for the last couple of lectures, deriving stuff and just like combining stuff we know to get simpler equations. And the second part is when we get the relativistic quantized open and closed string, and we can see how we get gravity back, how we get other particles back from that spectrum. We can also calculate some masses, and if we have time, we're gonna be able to show how this reproduces the entropy of a black hole. So that's the fun stuff. Right now, we're just deriving string theory, basically. And cool. It's like good to know all this stuff, because like usually whenever you start string theory, like for grad school, you start with grad school textbooks, and they don't really explain like where string theory comes from or like how people derive it. So yeah, it's a good start. The only bad thing, we're not gonna be able to do like all the fun stuff that is string interactions and all of that, because that requires having taken QFT1, QFT2. It's okay. We still know some string theory, the basics. And most people in the advanced graduate courses don't know the basics, because they skip directly to the to like already having the action and just deriving stuff with the action, and then they do CFT, and then yeah, you go into other routes. But now we're doing derivations from like bottom up, pretty much. Cool. So the 4 fundamental string equations we're gonna use is first the wave equation, which we already knew. Then the parameterization condition 1, which is just that we want tau to be transferred to sigma. That was what we were using. The parameterization condition 2, which is the one we just derived, that is making each part of the string having like a continuous uniform energy. That's good. And the boundary conditions are simplified now to just be this. That being like the partial derivative of the spatial component has to vanish at the endpoints. So that's cool. And then the string energy is just gonna be like we define the sigma 1 to be the full string energy. And there are some useful expressions. These are 3 useful expressions we're gonna use. And if you remember from our first lectures, or like the 4th lecture, maybe it was the lecture before, I'm not sure, but we had like huge expressions for p tau, and p sigma, and now the expressions are very simplified. So that's a win. That's a good thing for us. Cool. Okay, now that we have derived the equation of motion, now we want to solve them. So that's cool. With all the stuff we've done so far, so now we want to analyze what is the general motion of an open string. Like what's up with an open string. Cool. Okay, so I'm gonna just start with an ansatz, saying that we can write the string coordinates as being the sum of 2 functions. This is a non-trivial step, but like if you take a waves course, then you probably know the reason why we can do this. And if you haven't, then you can think about it as a string or a type of wave can be constructed as one wave going this way and one wave going this way, and with different functional forms, like with different shapes, basically. That's like the main argument of why we can use the ansatz to solve a wave equation. So cool. This is a very useful ansatz. Whenever you see a wave equation in any course you're gonna see in life, either 201, 302, or I don't know, partial differential equations, and I guess later in even in QFT, there's sometimes that you can use this trick. But yeah, whenever you have a wave equation, you can do this. And most of the stuff in our lives are gonna be wave equations. So, okay, cool. So now from these ansatz, we're gonna derive conditions for f and for g, which are just arbitrary functions. So f and g are arbitrary vector functions. Cool. Okay. Let me... How do we do this? Okay, there's going to be a bunch of derivations. Let me see if I have time to finish, because I want to finish... Oof. Okay, this is going to be tough. Okay. Let me do this just showing you like the steps. And we're going to do some important, very important stuff later. Like, we're going to do the derivation very quick right now. And I'm going to show you an example during class, like in-person class, next week. Cool. Okay, so for the boundary conditions, we're just using, basically, what I'm going to do here, take these ansatz, apply every single equation here, and derive some condition, like some equation that tells me, okay, this is the restriction for my functional f and g. Okay, cool. So the first boundary conditions for this open string is that this thing has to vanish at the endpoint. So what this gives you is if you take a partial derivative, you get this. Cool. Then you can just put these derivatives in this form, and then from here you can just integrate, and then you can see that g has to be f, but with a constant of with a offset. Cool. So then we can replace this into our original equation, and we just redefine f to absorb this part. If you don't know what it means, it's essentially just saying that f is equal to f, I think it's f plus a naught 2. You could say prime, but yeah, basically we're just absorbing into the definition. You've probably done this in some class, so cool. Just redefine f so that you don't have the a's there. Cool. Then we do the second boundary condition. But the good thing of this, now the equation is more simplified. Now we know that we only need to know f, we don't need g, so that's good. The second boundary condition in the other endpoint is going to give us another important condition. So we do the same. Take a partial derivative, we evaluate it at sigma 1, and then we substitute for a u parameter, and basically we have the derivative, we integrate, and from the integral we get that our f has to be quasi-periodic. By quasi-periodic, I mean it has to be periodic, but each time has a period, it increases by a certain amount, by a constant offset. So yeah, essentially has a period of 2 sigma 1, and it changes by a constant. Cool. Okay, so this is our second equation, or a second condition that we derive. And then we can use the two parameterization conditions, these two equations, this guy, where's this guy and this guy. And what we're gonna do is sum and subtract them. So we're gonna add and subtract these two conditions. We get this huge equation. If you can see, this is a, I don't know how you go in English, but you know, you can do the square and then put it inside the square. So we put it inside the square, cool. And yeah, then we can replace, yeah. So if you calculate these two quantities, you do this partial and you do this partial, this is gonna give you this, that is the derivative, space derivative with respect to the functional. And this is just telling you, like, this thing is telling us that the derivative with respect to u, this u parameter, is going to be a unit vector. So essentially, u is just a length parameter along f, which is our functional form. Yeah, this one, if it didn't make sense, make sure to look at the notes more carefully, and it's going to make sense. It's also in the textbook, but yeah, I'm trying to skip these derivations because it's going to take a while. Okay, if we combine all this analysis, then I just summarize here all the equations. First, we have the form of our string coordinates with respect to this f functional. Then we know that's a unit vector by the last thing we did. And we also know that it has to be quasi-periodic. Cool. So those are the three conditions for any open string. If you want to see a picture of how this looks like, cool. The picture is a quasi-periodic function is essentially the same, but each time there's like a new period, there's like some constant vector offset. So this is like increasing a bit. Bam, bam, bam. And it just continues. And yeah, and this derivative has to be a unit vector, and cool. So yeah, so each time it changes by this amount, this f changes by this amount, then we're gonna get an offset of 2 sigma 1. Cool. Okay. Another important thing from this string is that if we look only at the sigma 0 of one of the endpoints, we just look at one endpoint. Then if you observe this endpoint for u over c time, then you're going to be able to determine all the motion of the string, which essentially means like this motion is going to repeat for each endpoint. So it's enough to observe one of the endpoints to know all the motion of the string, which is crazy because that's going to have implications later. But for now, yeah, you just take this fact that you just have to look to one of the endpoints to know all the motion of the string. Cool. Okay, and the physical interpretation of b naught, this parameter that we introduced all the way here. We introduce a a b naught parameter. This is just the average velocity at any point of the string over the time interval of 2 sigma 1 over c. Basically what this means is that if you take any point of the string and then you let 2 sigma 1 over c time go, like that amount of time, then that's going to be the average velocity. And also it indicates, like if you see from one period to the other, it indicates overall how the string is moving, like towards what direction the string is moving. So you can also think of b naught to be saying what is the velocity at which the string is going. So that's another physical interpretation. And cool. And this is how much time you should observe your string to be able to reconstruct this functional form. So essentially, now that we have solved like the general motion of the string, we just have to find what is this f to be able to determine all the motion. So that's cool. And we're gonna do that in next lecture. At the beginning of the lecture, we're gonna derive what is this general motion for an example. I was actually making the notes, so it's just an example of how the string that's rotating, and we're gonna have to derive a bunch of stuff. But in order to make it complete, I want to go first through charges and like worldsheet currents and Noether's theorem, symmetries in general. Cool. So now we're gonna finally understand what these two quantities mean, what big P tau and what big P sigma mean. They're gonna be momentum, spoiler alert, essentially. Cool. So you're probably familiar with the electric charge conservation, which is just this. Like over time, charge doesn't change. This happens in some physical systems. If you take like all the universe, then charge shouldn't change. This electric charge. And now we can consider now forget about electric charge. Now we're going to consider any type of charge. So consider rho to be the charge density, and this J is going to be their current density. We can combine it into a 4-vector. The 4-vector is going to be this one. It's going to be our 4-vector, which is going to have C, rho, and the current, the spatial current. Cool. So a conserved current, like this in our definition, is going to be a conserved current if it satisfies this equation, which essentially is just a continuity equation. If you want to see why it's a continuity equation, you just separate it into the time component and the space component, and then we get this familiar equation. You've probably seen it in some class, like even in mechanics, I think there's some point where they do continuity equations. But basically this is just telling you that the only way to change the charge density in some region is you have to have some current, some input or output of charge. So cool. And if you want to look at the charge, the definition of a charge is just going to be integrating over the charge density over all the volume, or the same is just taking the first component of our 4-vector current and integrating over the volume. Cool. So then if we do charge conservation, you can take a time derivative of this charge, and this is going to give you the partial inside the integral. You can swap the integrals and the partials here. We're assuming a bunch of stuff about our function, but it's okay. Cool. So using the equation above, we're basically just using the continuity equation. We replace it here, and we apply the divergence theorem. Cool. Maybe I'll start doing this. I think this is going to be faster and probably more understandable than me just writing every single thing every time. So the divergence theorem is we applied here, and then we get this. So usually if we take a volume that is huge, then we assume that the charge, or like the current, vanishes at the surface, like whatever surface you're taking, and that's going to give you charge conservation. So if you assume you take the whole universe, then the current vanishes at infinity, then you get charge conservation. So yeah, essentially what we just show here is that if you take a continuity equation, or if you take this definition of charge, what is the meaning of charge conservation? Which is if a charge Q satisfies this equation, it is conserved. Cool. We already knew this, but yeah, just double checking. Cool. So now the important part is gonna doing charges, but using Lagrangian symmetries. So this is our Lagrangian, and we can write it in this form. Why we can write it in this form? If you see, we have like some infinitesimal constant, and we're gonna have some function. So you can always do this with infinitesimal transformations. There is a big, there's not a really big explanation. It's just you can put whatever transformation you're doing, this is just a transformation, into one function. Like it's just a function. Cool. And if our Lagrangian, this is gonna be super important, is left invariant after applying a transformation, we're gonna call it a symmetry transformation. That's the whole definition of our symmetry. And now we're gonna go into Noether's theorem. The baby version is that if the Lagrangian is invariant for the transformation for this transformation, or like this is just a general transformation, then the quantity, this quantity, Q, is conserved over time. So cool. And there's a proof. The proof you're gonna do in your homework, which is gonna basically be following the book of why this is true. And yeah, this is just Noether's theorem. You're gonna see this over and over again. So yeah, this is the baby version. We're gonna use the adult version in 1 second. And one example of how we can use this is that consider we have a Lagrangian that only depends on the Q dot component. So this is like the velocity component of any coordinate, and doesn't depend on Q. So essentially, if you do this transformation of Q going to Q plus some constant, then it leaves Lagrangian invariant. Why? This is a question for you guys. Why? Imagine you do this transformation. Why would you leave the Lagrangian invariant? Think about it. Cool. Basically, you're just taking a time derivative. So when you take a time derivative, this becomes 0. So that's good. And then you just plug in what is delta Q into our formula here. And this allows you to calculate the charge. So here we can calculate the charge. And the charge is just momentum. So we showed something very important, and for the ones that have taken physics 301, you remember this. From classical mechanics, whenever a coordinate Q is not present in the Lagrangian, which is basically this, like the Lagrangian doesn't depend on Q, then the conjugate momentum, or just the momentum of that coordinate, is conserved. Cool. So that's great. Okay, now the adult version, the one we care about. So consider we already done this before. So we have an action, but now we have a Lagrangian density. So we're integrating over time and also over all the spatial components. So cool. And A here is going to denote different fields. So this Lagrangian can depend either in the fields or the derivatives of the fields. Cool. So that's good. So now we're going to consider a transformation. This transformation is going to take our field to our field plus some offset, some like variation of the field. And now we can write analogous to what we did above here. We can write constants times some function to be our transformation. And this I is going to label different transformations. So each transformation is going to have an I. If you're doing only one transformation, this is just going to be like this. But if you do multiple, you use Einstein notation and you add up all the different symmetry transformations. Cool. Okay, then we can use Noether's theorem to say the following. This is like the adult version of Noether's theorem, the one you're going to use over and over again throughout your life. Is if the Lagrangian density is left invariant under the transformation, under this transformation, then the currents are conserved. Like these currents are going to be conserved, and the formula for the currents is going to be this. And conservation, or like the continuity equation, expressed in this form. Just taking a partial and adding up different indices. Cool. And you see there's a bunch of indices already. So I is going to denote different currents here, and alpha is going to denote components of the currents, just to make sure there's a distinction. So I can be like however many currents you have, 1, 2, 3, and then components is going to be, as always, 0, 1, 2, and 3, like the 4 vector components. If you want to know the charge, then you just integrate over the 0 component of your currents. So that's going to be your charges. Okay, cool. So now we go to the worksheet. We go to string, relativistic string again, and our action is just going to depend on the tau derivative and also on the sigma derivative. So that's what we're writing here. And one transformation that we can do that leaves the Lagrangian density invariant is just doing an offset. This is just a constant. So ask why it leaves the Lagrangian invariant. You just have to think about like what the Lagrangian depends on. Cool. This is a class question, so you should think about it. Now you think about it, we're taking derivatives, so a constant just goes off whenever we take a derivative. That's the right answer. And we can use our formula here, Noether's theorem, to derive the currents. So using Noether's theorem, we derive the current. I'm just replacing here. We know this this partial L, partial with respect to some derivative. That was our definition of big P tau and big P sigma. So essentially the two conserved currents for the relativistic string are these two big P and big P sigma, P sigma tau and P tau and P sigma. So if you do the conservation law, or like the continuity equation, then we find the relativistic string equation. Cool. So that's cool. So this is telling us that the relativistic string equation is just an equation of continuity, and that's the concept of the equation, which is cool, because yeah, from the beginning we started like deriving it just using the Lagrangian and using Lorentz invariance and other types of invariance and reparametrization invariance, and we actually found a continuity equation that can be derived from just doing symmetries. Cool. And also this allows you to think of like what is the power of symmetries. Symmetries allow you to derive very complex equations very rapidly just by analyzing your Lagrangian and very general stuff. Yeah, here if you integrate over the sigma coordinate for P tau, then you get momentum, and essentially this is just telling us that the physical meaning of big P tau is the sigma density of space-time momentum carried by the string. What this means, just think about it as space-time momentum, and there's a density, and this is the sigma density, so it's like the density throughout the string of momentum. And we can also show, this is a huge derivation, like takes 3 pages, that you can also write the charge in this way. So this is a formula you just have to keep in mind. Yeah, I'm not gonna do the derivation. There is 4 pages in CBAC if you want to see that derivation, but it's just telling you that you can integrate over a curve, and you just do this. Yeah, just take this form. Cool. We're gonna use this formula over and over again, so it's gonna be important. Okay, so we can also do the same for Lorentz symmetries. So by construction, we know that the relativistic string is already Lorentz invariant. By this I mean that if we change Lorentz frames, then the action stays the same, which is good. But equations of motion stay the same, but you know, for Lorentz invariant purposes, also the Lagrangian stays the same. Cool. And the Lorentz transformation, if you remember from the first lecture, then the definition was that this quantity has to stay invariant, which is just saying that the dot product or the length, the space-time length of a vector has to stay invariant. And a way to derive this using some transformation is considering this transformation. This is a bit out of the hat, but yeah, you can use this transformation to transform the string coordinates. And then we also want this quantity, the space-time length, to be to take any variation of this quantity and be equal to 0. So from here we can just do variational calculus, which is take a derivative, then we get this, which is just the variation. We replace the variation here, and then we get this equation, which has to be equal to 0. So essentially this equation is just implying that this epsilon mu rho has to be antisymmetric. Why? Also class question. The reason it has to be antisymmetric is that this part is symmetric. So you imagine swapping the indices, nothing happens, and then you wouldn't be able to get 0. but there has to be like some antisymmetric part to this whole quantity in order for this whole thing to be 0. So that antisymmetric thing is this epsilon. So essentially, the new definition of infinitesimal Lorentz transformation is going to be that it's any transformation of the form of this form that has an epsilon mu nu that is antisymmetric. Cool. So that's our new definition for infinitesimal Lorentz transformation. Okay. So we can also apply Noether's theorem, same formula, just plug it in, and we find that we have currents, and our currents are going to have this form. That is going to be the string coordinates times the momentum minus the string coordinates times the momentum. Essentially, we have these different currents. I know there's a bunch of indices, and also you can show just by construction, by having this thing to be antisymmetric, then the currents are also going to be antisymmetric. And you can integrate over these currents to get a charge, and we get these charges, which are the Lorentz charges. And the important part of what are these charges, like what do they mean physically, is that if you take the 0 to I charges, like which is basically the first row and all the first row of your Lorentz charges matrix, these are the 3 boosts, and ij are the 3 rotations. So as we knew already, Lorentz transformations are just 3 boosts and 3 rotations, and all the other components of this 16 by 16 matrix are just repeated from these 6 components. Cool. And why is this important? These charges allows us to get angular momentum. So we can calculate the angular momentum just to be in this form. I'm just giving you a bunch of formulas that I'm not going to show where they come from because that would take a while. But yeah, I'm trying to get you the main formulas to do the example next class. Cool. And then the string angular momentum is just going to be written like this. 1/2, we have this object. I'm going to show you in 1 second what it is. And we have our charges. Okay, so you have like any rotation from 1 to 3, 3 to 3, 1, 2. Basically, you're rotating the numbers. Then it stays at 1. If you swap any of these numbers, then you get, for example, 3, 2 here. This is -1. And if you have like any repetition of numbers like 1, 1, 2 or 1, 3, 3, then this is 0. So that's the definition. This has a bunch of components, but yeah, that's a 3 tensor if you want to think about it. But yeah, it just allows you to define what is the angular momentum with respect to the Lorentz charges. And cool. So that's pretty much what we're gonna see today. Yeah, just make sure to look at the boxes. Just look at the boxes, and that's the main result. Because the derivations are pretty lengthy and not really relevant to what we intend to do. That is, focus on getting the strings to show you the spectrum. We want to see like how the particles emerge from the string spectrum. And yeah, cool.